Hi, I'm Mark Madison, the historian at the National Conservation Training Center here in Shepherdstown, West Virginia. And I'd like to welcome you to another in our series of Conservationists in Action, where we have distinguished scientists, writers. Today we have somebody who's both, which is wonderful for us, come in and tell us about their research, what they're working on, and share any recent publications. And today we're very fortunate to have Dr. Cristina Eisenberg with us. Her most recent book is called The Wolf's Tooth: Keystone Predators, Tropic Cascades, and Biodiversity. It's a book we had the opportunity to recently discuss on our Wild Read book discussion, online book discussion forum we have out here at the National Conservation Training Center. She's been very kind to spend the morning with us, educating us about wolves and predators and so on. So Cristina, welcome to NCTC. It's great to have you here.
It's wonderful to be here.
And before Cristina tells you everything you want to know and need to know about top predators, keystone predators, perhaps you could give us a little background on how you came to be a conservation biologist.
Well, about 20 years ago, I moved to Montana. We live in a log cabin that is in a remote northwest Montana valley that backs up to the Bob Marshall Wilderness. And we saw wolves recolonize the area where we live, naturally coming down from Yellowstone. And when that happened, very shortly, everything changed. We used to have this big meadow on our land, and we used to watch deer and elk complacently browsing at dusk, and we thought that was really cool because they were beautiful to watch. But when wolves came back, the elk and deer couldn't stand around anymore or they'd get eaten. And they started moving and being very wary. And within 5 years, our meadow was gone. These shrubs and saplings that were ankle high got to be 7-8 feet tall. And so seeing those profound changes happen, we still had lots of deer and elk. They were just behaving very differently. Inspired me to go back to school and study these relationships as a scientist, and inspired my book, The Wolf's Tooth.
That's great. And currently you're a conservation biologist at Oregon State University, the
Yes.
College of Forestry, and a Boone and Crockett Fellow, so you've got a perfect background for this place.
Yes, and I'm continuing to look into the impacts of apex predators on ecosystems, and as a scientist in the context of those relationships, I'm also working on my next book, which is about large carnivores.
Great. We'll have you back for that too, if you're willing.
I would love to come.
All right.
Yes.
All right, we're going to have Cristina talk a bit about what's in the book, although I strongly recommend you buy and read the book yourself. It's very rich. It's got everything from environmental history to some of the current understanding and controversy about the role of predators in ecosystems. And it's also a very good read. It's enlivened by your field work and personal anecdotes and so on. So it's a wonderful book. It was a great book for Wild Read. It's a good book for anybody to read. But as Cristina explains some of her research and the book, please do feel free to contact us with questions. There's email, phone number, fax. If you have any questions that arise, please send them to us, and we'll be happy. I say we, Cristina will be happy to answer them for you.
Happy to interact with readers, with managers, with practitioners, with members of the public who are curious about these relationships. And I'm especially interested in talking about how one can apply these ideas that I'm going to talk about, these ecological relationships, to wildlife management and habitat restoration.
Great. So call in or email in with your questions, and Cristina, tell us a little about what you've discovered.
Well, my work is about ecological relationships, and my inquiry started out with Aldo Leopold's work. I did a lot of archival research trying to understand how our relationships shifted with these large carnivores. And I explore these historical contexts in my book, The Wolf's Tooth, and in my next book, The Carnivore Way, which will be out in 2013, I talk about how these relationships play out throughout the western United States with all the large species of carnivores. And here is, in a nutshell, what happened. This image that you see on the left is the ranges of carnivores in 1750. This is from Andrea La Liberté's work. And so there are 11 species of large carnivores, and you can see they're well distributed throughout North America. As of 2004, this is what those ranges look like. So the ecological impacts of those range contractions, which were primarily caused by harvest by humans, now we know that they can be profound. And Aldo Leopold was among the first to start looking into that. The U.S. Biological Survey was in charge of predator extirpation in the early 1900s, although it had been going on for a long time, and common wisdom then was that the only good predator was a dead predator. We had no reason to believe otherwise. So we hadn't quite succeeded, and so the government got involved in helping with this process. Here is what we did to the gray wolf as an example. There were formerly as many as 200,000 gray wolves in the lower 48 United States. This is based on Ripple and Beschta's work using government data, USFWS data. But by 1920 or so, we had reduced their numbers to almost nothing. And then you can see that their numbers start to go up around the 1970s through natural recolonizations coming down from Canada, and also due to reintroduction towards 1995. And Aldo Leopold, here he is. This is probably his first week on the job. He's heading out to cruise timber with his men. He had a brand new master's in forestry. He was a second graduating class at Yale School of Forestry. He was mentored by Gifford Pinchot. He believed that sustainable yield of not just trees, but wildlife that we harvest was his mission. And so he was cruising timber then, and also his job was to kill all the varmints that he found. This was in the southwestern US, so that would be grizzly bears and wolves, anything with sharp teeth and claws. So how did he get to that, from that to advising people to restore carnivores? Well, he may have started to question the wisdom of shooting every wolf back in the 1910s, but really he was influenced by a variety of other thinkers, such as Charles Elton. He was one of the founding fathers of ecology, Joseph Grinnell, Adolf and Ola Smury, Lee Dice, George Wright. All these people were gathered together in 1924 at a Mammalogists meeting. And the purpose of the meeting was to look at wildlife populations and their cycles. And these were the people that were doing top work in that field. And at this meeting, all of the people I just mentioned presented papers arguing for a carnivore predator conservation, and they actually signed a formal statement supporting this. So some of these people went on to do seminal work for government agencies. They were young and on fire with these new ideas about ecology. They forged relationships at this meeting with Aldo Leopold that lasted a lifetime, and here is Aldo Leopold and Ola Smury 20 years later. So they became partners in conservation in many ways. Additional influences on Aldo Leopold's way of thinking was between 1924 and 1927, he surveyed game species that were in production, that were being hunted. So deer, elk, and game birds throughout the Midwest. And he started noticing patterns. Then in 1933, he became the first professor of wildlife at the University of Wisconsin in Madison, and he actually created the science of wildlife biology at that time. So at the same time, a couple years later, he bought the shack, which was a totally depleted property in Wisconsin, and he set about to restore it. And it was for the purpose of hunting. So he wanted to improve wildlife habitat. And he took a trip. He was invited to go to Germany to study German forests. And the relationship between the forests is particularly with huntable game, and game habitat. And what he found in Germany were these forests that had been heavily managed for 300 years, where all the predators had been eliminated, where a monoculture of trees had replaced a formerly mixed forest, and they were like ecological deserts. And the deer and the elk were stunted, they were runty, they were genetically not fit. So he got to see what happens when you eliminate predation over many, many generations. So then he went to northern Mexico in 1936 and 37. He was an avid hunter, and he went on a bow hunting trip with his brother and his son. And this is a part of Mexico where I am from, and where my family, in the Wolf's Tooth I write about how my grandfather had a ranch there. And it was so big it extended from horizon to horizon. And my dad, toward the end of his life, confessed to me that his job on this ranch was to shoot all the varmints to protect the cattle. And he told me this would have been the mid-30s, that he used to see wolves all the time. And he could never shoot one because there was something about them. And he never saw them bothering the cattle. But he could never tell his dad that, because his dad would have killed him. So. But when my dad heard that I wanted to study ecological relationships of wolves to whole food webs, he really encouraged me to do that, because he said it's very complicated and there's a lot we don't understand, and there's something about wolves that transcends just the wolf as a species. So what Leopold found on that same range was a robust deer population, lots of deer, a full suite of large carnivores, so not just wolves, but grizzly bears and cougars, very active predation, and the vegetation was flourishing. So the forests were healthy, the range conditions were really vibrant. He came home from that trip and wrote this journal article for the Journal of Forestry, where he wrote, "There are few American deer ranges where the total removal of deer predators seems justifiable or necessary." Then he proceeded to travel around North America and evaluate habitat in ranges where predators had been eliminated, which was most of North America. And here you see images from Utah, that's the top left. That is an exclosure, that's an aspen forest. You can see that on one side of the exclosure, those trees are being browsed down to nothing. This side where the deer and elk are excluded, that's where they're thriving. Image on the top right, that's a browse line in the upper Midwest caused by moose. Image on the bottom right, that is an exclosure, an aspen exclosure on the Kaibab, and that is a deer causing the damage. Outside of that exclosure, you can see the aspen are being browsed down to nothing. Same as the meadow on our land, these relationships. Although Leopold was observing them long ago. The image on the bottom left is Mexico. Look at those multiple age classes of trees. And Leopold observed a high density of ungulates, but they were moving around. And that enabled the vegetation to grow, not just yet, browsed heavily in one spot. So while all this was going on, this is about, he was making these observations about the science and the ecology, but he was also making observations about our human relationships to landscapes. And over a 12-year period, he created the simple statement that is in a Sand County Almanac: a thing is right when it tends to preserve the integrity, stability, and beauty of the biotic community. It is wrong when it tends otherwise. The land ethic embodies a lifetime spent afield, a lifetime of learning from his mistakes, and being humble enough to recognize that he was wrong, and learning from others. So he, in 1944, in his archives, I found correspondence where he recommended wolf reintroduction in Yellowstone. He was contracted to do a survey of the range conditions in the park. And in his summary of his survey, he recommended reintroducing wolves. He also recommended reintroducing wolves on Isle Royale. And I found correspondence, I found a thick folder in the archives at the University of Wisconsin where he is advocating and planning a wolf reintroduction in Isle Royale with Ola Smurey. So it took us another 50 years to get around to it, but we reintroduced wolves in Yellowstone, and that is one of the biggest success stories in terms of the application of the Endangered Species Act. And the Yellowstone situation created this natural experiment. So we have been looking at what are these relationships about? What happens when wolves come back? And what happens is something called a trophic cascade. So this is a relationship among members of a food web. You have this top predator, this apex predator or keystone predator. People refer to it in different ways, but it's a predator that dominates that system. It influences the abundance and behavior of its prey, and it has a preferred prey species. And because it not only changes the density of its prey by killing it, but also its behavior, that in turn affects how things grow, such as what happened on our land in Montana. So these are all keystone predators. They occur in every system, and in the wolf's tooth I wrote about what happens in the deep oceans and in the rocky intertidal zone, and on the prairies and in grasslands and in coral reefs, rivers and lakes. Here you see a sea otter. You see Piesaster, which is a sea star, and the wolf, and they're all keystone predators. Here's Piesaster in the act. Piesaster consumes primarily mussels in Washington's rocky intertidal zone, the Washington coast. And so this keystone predator has a preferred prey. There's this very strong evolutionary linkage. And when you sever that linkage, then there's a domino effect through the whole food web, potentially. Some say that when you remove that keystone species, arches and ecosystems can fall apart. And Bob Payne, he's an ecologist at the University of Washington who created the term Tropic Cascade. He maintains that you can change the world really simply. All you do is get rid of one species. So here are some examples of these trophic cascades. These images are from James Estes' work in the Aleutian Islands, and you see that when you remove sea otters, sea urchins, which are the preferred prey of those otters, take over and they browse the kelp down to nothing. Kelp provides habitat for a variety of species, including many fish, and so when the kelp goes away, the fish go away. When you return sea otters to that system, you get these vibrant, healthy kelp forests, and biodiversity goes up. In Venezuela, John Terborgh had this natural experiment that was set up by building a dam. And so in this formerly dry landscape that had large predators in it, such as jaguars, it got flooded. And these islands were formed by the flooding because it was a hilly landscape. And there were big islands and small islands. And the small islands were too small to sustain any predators. So the bigger islands could sustain predators, and the forest looked like this. In the islands that were little, that could not sustain predators, this is what you got was what Terborgh refers to as an ecological meltdown, with biodiversity plummeting. You can see the forest structure. So this is about structure and function. It's about processes. It's not a single species thing. It's that this cycling of energy that's created by, in part by predation, changes dramatically when predation goes away or is diminished. And so that supports a whole lot of other suites of species. In Yellowstone, Ripple and Beschta have looked at these responses in aspen communities and in willow communities. And here you see two images taken, the top one before wolves were in that system and the bottom one after wolves returned, about 2003. You see a big difference in those willows. However, there's another component to this story. There was another big change between 1997 and, say, 2003. The climate changed. In the northern Rocky Mountains, where I live, there are anywhere from 30 to 40% more frost-free days per year. And willows, they grow during those frost-free days. So they have a much longer, a 30 to 40% longer growing season. Maybe that is also influencing this new flush of growth. So food web theory encapsulates both stories. And really, there are two different philosophies about how ecosystems work. This is I'll start with the bottom-up approach that says that everything comes from energy from the sun, which enables plants to grow. Then that supports herbivores and that supports predators. So this is driven by photosynthesis. Everything, this energy flows into the system from the bottom up, and fire can increase the cycling of this energy. The top-down approach was the alternative approach, suggests that predators control the system. And so when you add predators to this system, that limits herbivore numbers and affects their behavior, releases plants from herbivory, and increases the cycling through the system. In this image, you see a wolf on a carcass of an elk, and that carcass is also feeding all these other species. So there is this tremendous flush of energy through that whole system that this causes.
Cristina?
Yes?
That's the cover of your book.
That is.
Where'd you get that image?
My publisher got that image, and that was taken in Yellowstone. I have other images I will show you that were taken.
I enjoy it a lot. It
yeah,
actually makes for a striking book cover, I think.
The story is all there. That's the mark of the wolf's tooth. It affects the whole food web. Yes.
Great. Sorry for the interjection, but
so,
I had to know
no,
that.
That's great. So I wanted to know, how does this work? And there's this false dichotomy. Nature isn't black or white. It isn't bottom up or top down. It can be both. So I wanted to know, could it be both? And if so, how might these relationships, these forces interact? And I wanted to know specifically what effect would wolves have on ecological communities, and if so, how might context influence those wolf effects? So these images, some are from my study. One is from Yellowstone. The wolf, where the pack, you see that pack of wolves on the left, that's Yellowstone, and this image was taken not so long ago. And you look at the aspen in the background, and there aren't very many young aspen growing into that stand, even though there's a very active wolf pack. This is in the Lamar Valley. There's a remote camera image from the Northern Rockies that shows an elk successfully warding off a wolf. So wolves affect elk behavior in many different ways. And what happens when you throw fire into this mix? Fire is that other keystone energy that is evolutionary. It's been in systems for millennia. So the bottom image is a meadow that burned severely. It's the area where wolves first returned in Glacier National Park. I'm standing in the far lower right-hand corner of that image, and at a rendezvous site. And my radio-collared wolf data shows that the wolves are there a lot. So you see a trophic cascade, the vegetation, those aspen that ring that meadow are releasing and growing into that canopy. Is it a fire effect too, though? Or is this just because of the wolves? Those are some of the questions I started out with. So I created this conceptual model. That's
very simple.
Very simple. Yes, it's nature's tangled web, as Darwin referred to it. That's actually an interaction web. It shows all the relationships this is from a pelagic system from the North Atlantic. A food web is a gross simplification of that. It just shows who the key players are in that system. So in the system that I studied, I'm going to talk about what I learned in my research. You start with resources from the bottom up, the macro environment as I call it. So that's sunlight and moisture and potentially disturbance too. That enables aspen to grow. That then supports an elk population that's thriving, and that then supports wolves, the bottom-up perspective. Top-down, wolves are checking those elk, are controlling their numbers and their distribution, and that in turn is releasing the aspen from herbivory. When you add fire to that, that potentially creates this feedback loop. So how can you separate the effects of wolves from fire, or how can you determine how they interact together? Those are my questions. And these relationships, this simple food web, you're going to see it's really not so simple. It's pretty complex, actually. But it was these species were first identified as strong interactors by Charles Elton in 1927, Aldo Leopold in 1943, and other scientists. So these ideas are not new. So my PhD research was titled Complexity of Food Webs in a Large Mammal System. I worked with David Hibbs at Oregon State University. We wanted to examine the relative influence of top-down and bottom-up factors and the context dependence of these relationships. And we looked at 3 ecologically similar valleys in Glacier National Park, Montana, and Waterton Lakes National Park, Alberta. And because of human land use and wildlife management practices, they had 3 very different cases of wolf density. So the St. Mary Valley had a low wolf population. Outside the park is a ranching community where there has been depredation and wolves are not tolerated. And no pack has successfully recolonized that part of Glacier National Park in over 20 years. And it has not burned since 1880. The Waterton Valley has a moderate wolf population, and it has not burned since 1880 either. It has a single wolf pack that has been denning there since the early 1990s. Wolves have never been protected in Alberta. They are managed in a way that is very liberal. So landowners are allowed to harvest wolves for any reason, as long as they're within 8 kilometers of their land. And there's also a trapping season and a wolf hunting season. And so that creates a wolf population that's highly variable, but this wolf population is very resilient. So each year they den and produce a healthy litter of pups, and their numbers go up and down, but they continue to be present in that valley. And the North Fork on the west side of Glacier. It's a place that is not as well known as the Lamar, but it has a wolf density that is really, really high, possibly as high as the wolf density has been in the Lamar. It has burned multiple times portions of it since 1988. Other portions of it have not burned since 1880. And all sites have similar climate, soils, and plant communities, so they're ecologically the same. It's all foothills parkland ecoregion characterized by grasslands with patches of aspen, and it's all elk winter range. So I looked at all the elk winter range in both parks, and here is what my study site looks like, and you can see it's a very tough place to work. It's gorgeous. And here you see an elk herd. Waterton has a herd of about 1,200 elk. You see the aspen, the patches of aspen. This is the taken in January, so you see the snow is very light there. This is why it's elk winter range. It's a classic grass-dominated winter range. There are also elk winter ranges that are dominated by sagebrush or conifers, and for example, in northeastern Oregon. So this is a grass winter range. And grass is the elk's primary food. Aspen is the secondary food. It's a highly palatable food. It constitutes anywhere from 27 to 48% of elk's food in winter. They switch to eating aspen after they've consumed most of the grass. There are also shrubs in here. And that would be a third-ranked food choice in this system. And here's what the aspen look like in St. Mary, the low wolf area, Waterton, and the North Fork, the high wolf area. They all look the same. These are all the sites that didn't burn, and they are all characterized by this barren understory with very few aspen growing into the canopy, regardless of the wolf density. This stand down here is in the North Fork, where there's a lot of wolves, and it burned. And there you see something called recruitment. That's growth of aspen above the height that elk can eat. And I cored those trees. I measured their ages. The older trees date back to when wolves were extirpated from that area. The trees coming in, the younger trees, they date back to wolf return to that valley, to when wolves started denning there. And this image was actually taken very close to a wolf den in that park. Now, Ola Smurey went around the western states measuring what was happening with the aspen in Elk Winter Range. And this was 1923 through 1927, he determined, I found this in his field notes, that this was because we removed the wolves, which were the primary predator for those elk. Nothing else eats elk. Nothing else really preys on elk appreciably, significantly, other than wolves. Cougars, studies have shown that adult elk comprise less than 10% of cougar diet. In a variety of places, this seems to be the same pattern, and that wolves eat elk calves, but that's not going to significantly affect adult elk behavior. And bears, they take the calves. And so Murray discovered this in the 1920s, and he discovered these patterns of the barren aspen understories, but he did not look at the effects of fire. Fire was suppressed at about the same time as predators were suppressed. So management implications of this, Murray was trying to, his job, he was a manager working in Grand Teton National Park. And so he was trying to understand how the system worked. Today, we know a lot more about the importance of fire, for example, and so I incorporated that into my research. So we have these conceptual models that we used in evaluating these relationships. The bottom-up model, the red arrows indicate the primary forces in that system. And this is the model that was used in Yellowstone, actually. In this model, if you took wolves away, nothing would change. The system would keep operating just fine. Elk would be limited by their resources, by the plants available to them, and so they would reach a certain carrying capacity, and then their numbers would reach a point where they would be in some type of dynamic equilibrium with their habitat. Well, everybody knows that the natural regulation paradigm that was proposed and tested in Yellowstone didn't work. Those elk continued to increase in number exponentially, and range conditions continue to deteriorate. The top-down model suggests that wolves are controlling that system. And, you know, proponents of one model versus the other argue that this is how the world works, without considering that there might be a combination of these effects happening. So the image that you see there is of an aspen forest that has multiple age classes. It's a healthy forest. You see lots of young trees growing into the canopy. Although aspen regenerate episodically, here we have very vigorous growth, similar to what Leopold found in Mexico. This image is from a trail camera on my project. It's a top-down image at first glance. Here you see a wolf on the carcass of a deer. But what you see in the foreground are aspen. and they're being browsed to death in a system that has wolves, that has not burned. So now you see something like this. These aspen are highly unlikely to ever grow to look like the ones in the other picture where there's these multiple age classes. And you start to wonder about these relationships. How do they really work? And so I proposed this other model, which is a trophic trickle model, which trophic trickle is a scientific term that I write about in my book. It was first suggested in the late 1980s for systems where you may have this top predator, but it has these evolutionary and perhaps context-dependent relationships with other components of that food web. And so unless that context is all set up the way it has been historically, maybe there'll be a situation where that apex predator is unable to be fully effective. So to test these relationships, I looked at elk behavior, where they're spending their time, and you see these little vignettes of that model that show which components of the food web I looked at in these data sets by putting in pellet transects. I looked at elk and wolf interactions by doing focal animal observations, watching how vigilant those elk were. And I looked at the whole trophic cascade relationship by evaluating aspen demography. And I used very standard, classic, tested and true methods for all three of these data sets. And I applied multivariate analysis and modeling to these data. I also had collared elk and wolves. So the pellet transects involved pulling transects through that elk winter range through all different types of habitat in a way that we would capture the heterogeneity of that landscape that you saw in that image, those rolling hills. The data was ungulate pellet piles and large carnivore scats. The sample size, the transects were 50 meters by 2 meters. The sample size was enormous, as it has to be because of issues with overdispersion of the data. These data have been used by managers and people doing monitoring and surveying for decades, but in very small sample sizes. And this was before we had some of the multivariate methods we have today for analysis. These analysis tools enabled me to take this method and elevate it in rigor and apply very sophisticated modeling to it. And when I looked at these data, my findings were the same as the findings I got from my radio collared elk with GPS collars. So that was really interesting to find that a very low-cost survey method yielded the same results as collar data did, which cost hundreds of thousands of dollars to get. So the findings were elk density. In the literature, anything above four elk per square kilometer or higher is considered very high, and by high, they have, at that density, they can potentially have severe impacts on their winter range by overbrowsing and overgrazing. This has been widely documented by a variety of wildlife ecologists. Post-wolf recovery in Yellowstone in the year 2000, surveys reported elk densities of 6 to 13 per square kilometer. In St. Mary, I found 21 elk per square kilometer. In Waterton, 24 elk per square kilometer. In the North Fork, 9 elk per square kilometer where there had not been fire, and 8 elk per square kilometer where there was fire. So this suggests a density-mediated relationship where more wolves means fewer elk, certainly, but it also suggests that in the North Fork, where wolves have been established well since the mid-1980s, there's a dynamic equilibrium occurring where there are lots of wolves and lots of elk, and they are coexisting. And elk numbers in the North Fork are above management levels, management objectives. So, and this has been going on now for 30 years almost. So this is how it is. These data are from before the wolf hunt. So now this would be different. But this is an example of how these evolutionary relationships can play out across the landscape when there are not human land use issues that must moderate them. So predation risk, I looked at where elk were spending their time relative to how dangerous it was for them to be there, and I found some interesting things and had some really interesting experiences in the field. The image on the top left, what you see is this bench. And I had pulled a transect through there and categorized that as a high predation risk area, because if you're an elk there, you can't see what's on that bench. And what was on that bench was a carnivore trail that was marked every 20 meters or so with some type of large carnivore scat. Everything was up there, grizzlies and cougars and wolves, of course. So as I'm pulling this transect, the wolves took down that elk right on my transect line. I was 200 meters away, and I wrote about this in my book. And sure enough, in the bottom image, those are eskers created by glaciers, and you could see that rolling terrain makes it very hard for an elk standing where one of those surveyors is to see what might be on the other side. So these are view impediments. I also looked at impediments to escaping a wolf, debris. And now that image, I had surveyed that area the day before and categorized that as a high predation risk area because of all those impediments to running. Elk like to run with a stiff, open-legged gait. They don't stot like deer. I came back to work the next morning at 8 a.m. and there was an alpha female on a freshly killed elk carcass. And my field technician, Dave Moskowitz, shot that at about 50 meters. And that was an alpha female we didn't know existed because we had collared the other alpha female in that pack. So this is an example. That pack had 2 breeding pairs that year. Anyway, what I found was that the elk were avoiding those obstacles. They were also avoiding aspen stands, with the exception of the stands that had burned, and they were spending all their time there, and the elk were avoiding the stands that had burned. So there's that relationship, that Tropic Cascades relationship that has to do with predation risk. And these patterns were really graphic. They were boldly stamped on the landscape via the Pellet Transect data. I created 240 models, statistical models, to further explore these relationships and how things such as staying warm in winter, thermal regulation, the ability of the landscape to retain heat can affect where elk are spending their time, how food quality and type can affect the decisions that they make. And I found that predation risk is the primary driver of where elk are spending their time. So there's that component of the Trophic Cascade present. When I observed what elk were doing in terms of how much time they were spending being vigilant, I found a more complex story. I observed individuals continuously for 3 to 20 minutes. This is a very classic method that's been applied by many wildlife biologists in many places. A lot of this work done in Yellowstone. I measured time that they actually spent with their heads up. I stratified observations by social class. A cow with a calf will behave very differently than a bull elk. And I had a large sample size. And I found that in Waterton, where there aren't any wolves, in St. Mary, where there are no wolves, elk didn't respond to anything, any of the predation risk variables. I used multivariate analysis to evaluate all of the different things that have been identified as influencing elk behavior, such as proximity to roads, proximity to forest, ability to stay warm, thermal cover, and of course what the wolves were doing. And nothing was significant in St. Mary. In Waterton, the elk were highly responsive to predation risk factors. such as group size. The larger the group, the less vigilant they were because there's safety in numbers. And certainly the predation risk factors having to do with the escape impediments and view impediments. In the North Fork, though, where wolves were everywhere, the radio collars I had on wolves showed that they were there all the time, that if you're an elk in that valley, you can't ever get away from them. They're just there. The elk response was very different. So there, the larger the group, the more wary, the more vigilant those elk became. And that was a big surprise because in the literature, most people believe that, a large group means safety. But I dug into the literature more and found that other people have discovered these complex relationships. And so what happens in the North Fork is what others have found other places, that large groups, if there are lots of wolves, a large group of elk is much easier to detect if you're a wolf. Wolves use olfaction, their sense of smell primarily. And a small group can be harder to find by smell. So perhaps they've changed that strategy. And I also found that using multivariate analyses that these relationships were not linear, that in the North Fork there were interactions between variables having to do with predation risk, and so the elk would switch their strategy when the group got to a certain size or impediments got to a certain size. But the take-home message is that if the ecology of fear, as this has been called, by John Landry, who coined that term, is part of what drives a trophic cascade. Having a wolf population that's highly variable, as in Waterton, who the elk never know where those wolves are going to come from next. Those wolves are very skittish because they're harvested by humans, leads to pretty responsive elk to predation risk variables, versus an area where there's a saturated wolf population and those elk have to develop very different strategies to stay alive. And in management, we can incorporate some of these patterns of behavior that some of us are finding into making decisions about how to manage elk and how to manage wolves. Aspen demography, so here's the other piece of that story, the Tropic Cascades story. These are aspen. I used very classic forestry methods to measure how much they were being browsed and how they were growing. These images were taken in the North Fork at a wolf den. Same aspen stand. Part of it burned, part of it did not, has not burned since 1880. Where there has not been fire, at this wolf den where wolves are very active, you see a very different pattern than where there has been fire. So I looked at browsing by stand size and by plot position, whether plots were on the inside of the stand or the outside of the stand, inside of the stand being potentially riskier. I looked at the effects of moisture and heat retention, so the slope, how much sunlight a particular aspen stand got, the aspect. And I looked at the size classes of the aspen. Here are the young sprouts at about 1 meter. Here are the aspen that are recruiting about above browse height. There's a very strong story here. The big difference between these two images is fire. So what I started seeing is that perhaps there could be a trophic trickle happening here, that without that bottom-up keystone force, maybe that system, the keystone predator, even in very high densities, isn't able to fully trigger a trophic cascade. So I measured that, but first I looked at the effect of climate and soil and moisture on those aspen, because aspen are driven by those things, and I found that it was not statistically significant moisture, except for in St. Mary, and there it was not really significant, but it had a stronger effect. The big take-home message is that in all three valleys where there hadn't been fire, I found the same pattern of aspen demography. So the first set of bars on the left hand of each side of each figure are the young aspen that are 1 meter in height, followed by the ones that are between 1 meter and 2.5 meters. 2.5 meters is how high elk typically can browse. The third bar represents the trees that are recruiting, that are 2.5 meters in height to 5 centimeters diameter at breast height. They're the young pole-size aspen, the understory and mid-canopy of a forest. And the fourth bar, the one on the far right, those are the old aspen, senescent aspen. You see, if there were a trophic cascade, you'd see a big flush of growth in that third bar, and there isn't one where those aspen have not burned. The only place you see one is where they have burned. And so regardless of wolf population, without fire, those wolves are not fully driving that trophic cascade in this system. So back to this conceptual model. You see St. Mary and Waterton and the North Fork without fire all show the same patterns. The weight of the arrows shows the weight of those effects. The big difference is when you add fire. And you see the arrows are a lot heavier in the North Fork where there's been fire. You don't have to look at the details of these models, just squint your eyes and those arrows represent energy moving through a system. And you can see that fire greatly stimulates this energy flow. Now in my book I wrote about these relationships, including trophic trickles in oceans and streams and coral reefs. And so the complexity that has been well documented of these mark of these apex predators in these other systems, I was able to find the similar complexity in a system with wolves and elk. And so this is, my research just starts to look at the tip of that iceberg. And in moving forward with management of wolves, particularly post-delisting, these relationships can be incorporated by managers as they work to manage populations of both predators and their prey. And the survey methods I use, with the exception of the collars, are very inexpensive. They're classic, they're tested methods, they are easy to apply. So, and fire can be used, the message here, as a powerful management tool. So what I concluded was that elk response to predation risk is influenced by many things. It's not a simple elk-wolf thing. To understand elk response to wolf population level or density, you also need to understand the context of this relationship. So what I found in this system could be very different in another system, but I found the tools to measure those relationships. And other factors such as fire moderate the effects of wolf populations. So how can we apply these things to restoring ecological resilience and wildlife habitat on mixed-use lands? Resilience is a keyword that has come up a lot in the Forest Service uses it in its new rules. U.S. Fish and Wildlife Bureau Agency uses it in planning documents and EISs. As the climate continues to change, as habitat continues to become increasingly fragmented by growing human populations, maintaining resilience becomes more and more important. And it's about processes. So the processes I talked about in my book, how can we incorporate them in taking this whole ecosystem look at management? So how we can apply the science is start by considering the context. Work on a landscape scale. So not a single species scale, but a scale that incorporates those processes such as wildfire, such as predation that's active. Consider mimicking natural processes because it's impractical to have these processes in place in every management unit, every landscape. Monitor at regular intervals. So the methods that I use can be applied quite rapidly to monitor, and one can designate focal areas to monitor. So the benefits are that of this approach is that it's inexpensive. It measures these relationships, and the relationships have everything to do with how resilient a system is to perturbation, to fragmentation, to disease, to drought. It allows for consideration of context, and it can be applied to very targeted landscapes. So if there are landscapes of special concern, it goes way beyond a single species approach. For example, these concepts can be applied to addressing sudden aspen decline, and aspen provide very important habitat for birds, and they provide ecosystem services in the form of shading and helping maintain clean, clear water in watersheds, so at the watershed scale. Trophic Cascades relationships can be used for fire management, so helping us make decisions about prescribed fire, let's say, or where we will allow fire to burn and how. These awareness of these relationships can help us better understand how to address dispersal of apex predators. This image shows a wolf that dispersed from the greater Yellowstone ecosystem in, I believe this was 2009, and ended up in Colorado on the doorstep, literally, of a ranch, the High Lonesome Ranch, where I'm the research director. And this wolf made about a 1,000-mile dispersal. It was a tangled route, bounced around between Utah and Wyoming and Colorado. But this is one animal that had a collar. There are many others that are doing this that don't have collars. So these dispersals are quite active right now throughout the West. The High Lonesome Ranch is this astonishing landscape. It is located on the west slope of the Rocky Mountains in west central Colorado, 220 acres of deeded and permitted land. We own all the mineral rights. Paul R. Valdick started purchasing this land in 1994. And we are in the process of founding a Science and Conservation Institute based on Aldo Leopold's land ethic. This is quintessential, totally thrashed ranch land that we are applying Aldo Leopold's ideas to restore, and that involves taking a whole ecosystem, trophic cascades approach, so looking at all of those food web relationships. And Hal Salwasser is the Institute Consulting Director, and I direct research there. Here's where the ranch is. You can see all the red stuff on the map is sudden aspen decline. And you can see this is the path near where that wolf ended up. And what we're doing there is a lot of the stuff that Aldo Leopold did on his land and other things that Trophic Cascades researchers have incorporated. We're looking at aspen ecology and trophic cascades. I'm working with Michael Soule on that project. We're restoring aspen by treating them. We do not have an established wolf population there, so we're trying to mimic some of those keystone effects with things like hunting practices and hopefully fire soon. We have a riparian trophic cascades project. We're restoring a 17-mile reach of stream and reintroducing native cutthroat trout, working with 3 government agencies on that. We're undertaking rangeland restoration, and we have a native plants program. And we have, working with Wildlands Network, to start a private landowners network. Currently, there are 8.5 million acres of private lands in this program. These are conservation-minded ranch owners that are managing their ranches for mixed uses. So, and this is applying that land ethic because Aldo Leopold always stated that we are part of those lands, and those lands need to support humans, but we need to revision our relationship with those lands in order to figure out how to do that. So with that, I would like to thank the many people that have supported and informed my work and open this up for any questions or discussion.
We're kind of out of time now, Cristina. because you had so much wonderful stuff to cover. But I would encourage people that have questions, email them to us. We'll forward them to Cristina and get her to address them. Great presentation, wonderful field science you carried out, and some provocative questions for us to consider as public land managers. So thank you. We'll try to get you back.
Thank you so much.
Learn about the new book and how things are going at the Lonesome Ranch up there.
Thank you.
So thank you. Thank you all for tuning in, and we'll see you again next month.